Hi everyone, in this video we discuss subtopic 6.4. The last subtopic for this chapter is about conservation of angular momentum. Okay, so you need to be able to define and use angular momentum L equals to I omega and state and use the principal conservation of angular momentum. That one will be summation of L initial equals to L final. Okay, now if you guys still remember, just a little bit of recap, we have S, which is equivalent to theta in rotational motion, and then we have V, which is equivalent to omega, A, alpha, and then we have force, and then we have mass, and then we have momentum. So this one is very similar to top. Mass is I and P. Now we will discuss about L. Okay, so obviously you don't need to know, you don't have to derive the formula, but I just want to show you after this. Okay, first maybe we can go to the diagram here. It says that for a particle P of mass M travels in circle of radius R with tangential linear velocity as shown in figure below. So basically, for a particle P travels in circle radius R. So this is the P lah. Okay. With tangential velocity as shown as below. The angular momentum of the particle about the axis of rotation is given by L equals to. Okay, so this one is actually just the derivation. I'm gonna go through faster now. Okay, it comes from this formula because it's a cross product. So you have RP sine theta. Okay. And then since the P is equals to mv, so this one is actually, that is the formula. And then since we have P linear momentum, we have P equals to mv. You can substitute inside here, so it becomes this equation. And if I change to omega, we'll have this one, and mr squared is basically your I from previous subtopic. So the key formula that we will discuss in this chapter is L equals to I omega. Okay, this one is very important. Okay, angular momentum of a body rotating about phase as is the product of an body momentum of the inertia and its angular velocity. So basically the definition comes from the formula itself. If you just write the formula for definition, make sure you write down this one. Okay, where L is equals to angular momentum, moment I is moment of inertia, and omega is angular velocity. Okay, notice on the unit here. Okay, since angular momentum is a vector quantity, so obviously it will have a direction. So how to determine the direction? Okay, this is the example. This is an example. So you have the wheel which is rotating in that direction. So you can imagine that this wheel is rotating in that direction. So to determine the direction of angular momentum, you have to use right hand rules. Okay, right hand grip rule. So you have to put your fingers curling towards the direction of omega. So basically this one follows omega, while your thumb will be pointing towards the direction of L, which is angular momentum. Okay, so try this one, make sure you do it, and then maybe if you have a problem, you can ask me later. Okay, and then the second part is about conservation of angular momentum. So that I told you before, previously we have conservation of momentum. Now we are talking about conservation of angular momentum. And then it's very similar to the Pi initial to P final, except now we are talking about Li equals to L final. And since Li is basically I omega, so you end up with this one. Okay, but it depends on the question, and you have to read the question carefully lah. Okay, because of the magnitude of system, okay, we can express the principal conservation. Okay, so basically it says that if initially we have this I omega I, and finally we have I omega, so any of these, if it changes, you have a change in final. So example, let's say it's moving pretty slow, okay, but then suddenly this one goes down, and this will go up. So it depends on the information. Okay, example that demonstrates conservation of angular momentum. Okay, we have two main examples. I think you can go through. Okay, one is ice skating, another one is rotating platform. So if you are moving closer or further away, if the person moving closer or further away, what will change is actually the I. So if I is changing, so obviously omega will change as well, because the sum or the total is actually conserved, it doesn't change. And similarly, this one is ice skater, and then you can see that she changed the position of the hand. So when she actually bring it out like this, what happens is that the mass over here and the mass over there is actually increases. I mean, the moment of inertia is increases because I equals to mr square, right? So because of that, because of this action, the values for the values for L will be bigger. And if she closes her hand like this, what will happen is the radius will become closer. So moment of inertia is smaller, so you expect that omega will increase. So basically, if you want to move faster, you have to put your hands inside like this, minimals the I. You want to go slower, you open your hand like that. Okay, example that I'm going to discuss with you is actually question 14. After this, maybe you can try to do question 15 in tutorial. So a skater is spinning at 3 radius per second with both arms outstretched, so that she has a moment of inertia of 4 kg m square. The arms are now drawn in so that her new movement of inertia is 1.8 km square. Calculate her final angular velocity. So basically, I use the diagram from before because this one is perfect representative for the question. It says that initially it is spinning at 3 radian per second. That one will be omega naught. Don't forget to put naught. And then it says that, so this one is initial, this one is final. So the final, her arms drawn in. The moment of inertia initially when the arms are outstretched is 4 kg m square. So that is the I, moment of inertia. Her arms are now drawn in so that her new moment of inertia is 1.8. Calculate her final angular velocity. So you want to apply conservation of angular momentum. This one will be initial and this one will be final. Okay, remember, this part is initial and this part is final. So you guys need to know that formula for L is equals to I omega. So equals to I omega. Except this one is omega initial, this one is omega final. This one is initial I, this one is final I. Okay, so if I substitute all the values, I will get 4 times 3. So make sure everything is in SI unit, because final answer, then you can straight away write it in SI unit. Okay, so it will be okay. So basically the question wanted to find omega final. 6.67 radian per second. Okay, so that's it. Thank you.